Hi. Okay, hello everyone. Welcome to our INQA seminar series. And today we have the pleasure of hearing from David Ferguson from Northrop Grumman on requirements for non-stochasticity in superconducting circuits. Take it away.
Sure. So, so I've been working on quantum annealing for a long time.
David, sorry, just one thing. Would you be able to go to full screen?
Yes, I will.
Okay.
I just wanted to. Yep.
Thank you.
How about now? Is that giving you the full screen there?
That's right. Thanks.
Great. So, so I've been working on quantum annealing for I don't know, half a decade or so, and largely as part of Daniel's QEO program. And so these are kind of slides and results that we generated as part of that program. And actually, Paul Warburton is, of course, a big part of QEO as well. This talk is largely going to be hardware focused and talk about hardware that we designed probably about three or so years ago. Unfortunately, it's never been extensively tested. I am going to show some of the test results that we had on our non-stochastic chips. But I've put there in the chat some of the more recent talks. And the first one is by the Warburton group, where they kind of are talking about how these non-stochastic effects could be used, to enable quantum annealing. Another one there kind of talks about how to reduce quasi-particle noise, and which I'll talk about a bit in this talk. It kind of shows a qubit that has really showed, quasi-particle jumps. These charge E quasi-particle jumps really dramatically, with an hour-long time between quasi-particle jumps. So would really be enabling for this type of technology that I'm describing, as well as I think one of the more exciting research published in quantum annealing in quite a while, this recent paper by D-Wave, and I'll kind of touch on the relevance of that one, as well as, of course, Daniel and Elizabeth's kind of review article that kind of talk about diabatic quantum annealing, which in some ways is a bit of a competitor to non-stochastic hardware. But I think that that's a very interesting concept as to think about as to what the various ways of getting beyond efficiently simulatable quantum annealing systems, what do they enable for different frameworks. So with that as a preamble, I certainly welcome if somebody feels like I'm missing some talks, go ahead and add that to the chat and we can talk about it. So as I understand it, Daniel, this talk is scheduled for about a half an hour and then maybe 15 minutes for question and answers. Do I have the time frame right?
Actually, usually we go up to an hour, including questions. So feel free to
Okay.
go a little longer.
I'll go. Okay, sounds good. Well, that means I'll just kind of go through my slides a little bit slower, or just kind of. I welcome people to make questions or comments then, especially. So let's see here. It's really. Daniel, are you seeing the very top of my slides here?
I can see recent couplers have generated stochasticity allows the ground state. Okay,
so you do see. So my slide is blocking part of the title of the slides, but basically here's kind of some of the high level takeaways for the talk, in that stochasticity is a kind of a play on the words stochastic. And it kind of is a class of quantum hardware that allows classical systems to efficiently simulate its ground state. So basically, it is a class of Hamiltonians where that don't have a quote unquote sign problem, and such that you expect through quantum Monte Carlo to be able to efficiently simulate the ground state. However, It does not mean that when you have stochastic hardware, there can't be a quantum advantage. And so this has been a recent area of research. Some areas where you might get quantum advantage is that that you could see, a suppression of chaotic dynamics that would be there in the classical dynamics, but for the quantum dynamics are suppressed. So that could be a reason for kind of engineering into the quantum realm to engineer your hardware to have quantum effects. And of course, you have a phenomenon of quantum tunneling, which can dramatically enhance various transition weights. And so if you, again, engineer quantum system, or engineer hardware that operates in the quantum regime, you could have a beneficial behavior of that hardware using quantum effects that don't require stochasticity. That don't require non-stochasticity. So stochasticity still can have quantum effects that are advantageous for the hardware. However, if you do only have stochastic ground state hardware, it does likely mean that universal adiabatic quantum computing is impossible. So if you want to go for this goal of having, that you kind of remain in the ground state of your Hamiltonian, and you just kind of adiabatically morph the Hamiltonian, and such that you end up doing kind of adiabatic transformations of your ground state, and you want to implement universal quantum computing that way, it is likely that you can't just do that with stochastic hardware, that you are going to have to find some sort of way to engineer additional effects within your hardware, so that you make a transition from stochastic to non-stochastic hardware. And I'll explain how specific hardware that we designed that is intended to make some steps in this direction. All right. So of course, if stochastic hardware use excited states, then this can also enable universal quantum computing, and so that is a kind of a way around of using kind of stochastic superconducting circuits, but you end up using excited states. So so here is the key requirement for generating non-stochastic effects in superconducting hardware. And that's what this talk is all going to be regarding, is superconducting hardware. Of course, there's many other hardware that are, that different research groups are developing into quantum technologies. This talk will be kind of specifically referencing superconducting hardware. And I'll say it this way, that superconducting hardware must utilize a non-zero vector potential in the flux basis. So there is kind of a common thing that we learn in quantum mechanics as we're kind of learning it for the first time, that somehow to get non-trivial phases into the ground state, a lot of times we have our charged particle moving around and we have a vector potential that encodes the magnetic field. But for superconducting hardware, you actually end up using the basis is typically flux basis. It's typically your flux basis. So so instead of needing to have a non-trivial magnetic field, you end up needing to have non-trivial offset charges, and the phases that show up are due to Aharonov-Casher physics, not due to time reversal symmetry breaking and Aharonov-Bohm effects. Okay, so there have been a lot of attempts over the years to how to make non-stochastic couplers using existing flux qubit concepts. And so I've drawn over here on the right-hand side, I've drawn two kind of conventional tunable flux qubits, the kind that are used in annealing. And I've drawn this blue capacitor between them. And there was kind of and there was a study. I didn't get a chance to update all of these, any of these references here, but I'm sure you can find the published papers that are referenced here. So basically, you get this capacitive between two flux qubits, and there's kind of a notion in which this indeed does generate some small residual non-stochastic effects, and I'll kind of talk about that in detail. But it doesn't kind of fundamentally generate non-stochastic effects, and I'll kind of explain what I mean there. And here's another one where in the bottom panel, where instead of kind of having a tunable interaction, tunable coupler interaction, that's kind of a tunable mutual coupler there shown in blue, between the kind of the main current that kind of flows in the main loop of the flux qubit. Maybe you want to create interactions between the current that's flowing within the tuning, the compound junction loop of these qubits. And that was another kind of concept for how you might get non-stochastic coupling. And both of these approaches basically proved to not be all that effective at generating non-stochastic effects when those coupler types were between conventional flux qubits. However, when you kind of generalize these flux qubits to these Josephson phase Philip qubits that I'll describe later, that kind of intrinsically utilize offset charges and therefore have non-zero vector potential, in that context, these exact couplers can be effective at generating strong non-stochastic interactions between the constituents flux qubits. So the way that I came to kind of understand that even when you have basically stochastic Hamiltonians, you could still nevertheless get small residual fundamentally non-stochastic interactions is with this paper by D-Wave and this kind of very simple 3-level model. So this 3-level model is basically designed to kind of represent this Z operator. Basically represents the kind of the current that's flowing in the loop of the current of a qubit. Maybe it can have negative or positive current or no current, and then this D operator is basically a discrete derivative like operator. And of course, in quantum mechanics, when you have the derivative with respect to flux, that corresponds to a charge operator in your system. So basically, this Hamiltonian that's shown there is a 3-level kind of a discrete analog of a very simple LC oscillator, kind of like a Q squared plus L squared, Q squared plus flux squared type of Hamiltonian. And it's fundamentally stochastic. So what does stochastic mean? It means that all of your off-diagonal terms in your Hamiltonian, if you find a certain basis, which means you kind of do local unitary transformations, you can kind of reveal that the Hamiltonian has this form where it has diagonal values, but all off-diagonal values are non-positive or negative. And when you have this, you can basically show that the ground state for such Hamiltonians, they don't have any nodes, and so therefore you can kind of use quantum Monte Carlo efficiently to find the ground state. So, however, when you basically diagonalize this Hamiltonian and you kind of choose a new basis, and in this case, because you're dealing with the 3-level system, you have some arbitrary unitary that basically reveals the 2-level approximation. So you've taken a higher level, higher dimensional subspace, and you've kind of reduced it down to its essential 2-level approximation. And of course, this type of 2-level approximation is very familiar from the context of D-Wave. We kind of do that kind of 2-level approximation from a larger defining Hamiltonian all the time. And so what one of the interesting things is that now, if you go to the Hamiltonian and you just kind of put 2 of these qubits, so H1 and H2, and then you include interactions between these 2 kind of discrete stochastic qubits, these 3-level systems, and you include some capacitive interactions, i.e. some charge-charge interactions between these 2 qubits, as well as simultaneously magnetic flux-flux interactions, you still see that as long as you choose the proper representation for the charge operator, you see that indeed that the Hamiltonian, here it's kind of, here are all the numerical values, and you can kind of go term by term to check that all of the off-diagonal terms here, if I just look at the sign of those terms, you see that all the off-diagonal terms are indeed negative. However, when you go through and you then apply these unitaries, these unitaries that reduce from a 3-level system down to a 2-level system, you do find that that the effective Hamiltonian that kind of just describes this low energy subspace, this kind of 2x2 low energy subspace of the qubit, they do have positive off-diagonal terms. And you can reproduce basically exactly what they saw experimentally in the D-Wave system, where you kind of use this these kind of effective Hamiltonian techniques, which had a recent paper by the Warburton group, where they kind of developed this stuff in more detail. But basically, it shows this 3-level system shows the exact same effects, that in this region you get you get a small residual non-stochastic interaction that you can't really cure by just doing a unitary transformation of just those 2 levels of your qubit system. So somehow, if you really wanted to cure this system, you would have to increase your Hamiltonian. First of all, you'd kind of have to include this larger subspace that you're basically neglecting in your low energy subspace. And then you'd have to kind of generalize the unitary transformation, the kind of the local unitary transformations that you are allowing to include not just 2-level transformations, but 3-level transformations. So this was really surprising to me that somehow that you could have a 2-level approximation to to your stochastic Hamiltonian, and you could have non-curable non-stochastic interactions between these qubits, but they were kind of somehow small and residual. And if you then kind of said, well, I'm going to allow in my definition of local unitary transformations, then you did indeed find that actually, yes, there is some local unitary transformations. In this case, a 3x3 a local unitary transformation that can cure this this Hamiltonian. So this kind of multi-level curing is a kind of a generalization of the concept of 2-level curing. But as far as I'm aware, there's no kind of general theory that kind of looks at a fundamentally non-stochastic Hamiltonian in the 2-level description and figures out a way to kind of say, hey, well, this one is going to be 3-level curable, this one's going to be 4-level curable, or whatever it is. But the one thing that is true is that you always do get, even though you do have these kind of fundamentally non-stochastic terms, they are kind of small, and they don't really they aren't the dominant terms in the Hamiltonian. Okay, so I kind of want to tell the story that I told the story to kind of recap some of the surprising things that I was learning about non-stochasticity in these systems, and what it fundamentally took from a hardware perspective to really engineer in non-stochasticities into these systems. So it can
David,
kind of be
quick question.
You
were referring to levels, 3-level and so on.
Yeah.
Could you clarify the language there? Are we talking about levels, qubits? Because this Hamiltonian H effective is 9x9, right? If I'm counting correctly. So
yes.
yeah,
sure, go ahead. And so of course the actual this is a discrete representation of a continuous variable Hamiltonian. So the actual flux and charge variables of superconducting flux qubits, of course, are continuous variables. It's similar to the position variables of helium-3 as it kind of, or sorry, not helium-3, helium-4, the bosonic helium-4 are just kind of continuous variables. And when you do a numerical simulation, you just choose a discrete basis. And the accuracy that you want to simulate with, you kind of have to increase the number of states that you're including more and more and more to get higher and higher accuracy. Here, I've kind of, for simplistic purposes, I've chosen just a 3-level approximation to the flux operator and to the charge operator. And then I have the full stochastic 9x9. But then I use these unitary transformation that took the 3x3 to a 2-level approximation, at the single qubit Hamiltonians. So basically, I took this kind of bigger 9x9 Hamiltonian, and then I applied the single qubit unitaries that took H1 and H2 to the to a 2-level approximation. And of course, you have the remaining interaction terms as well, and those ones you kind of handle with using these kind of effective Hamiltonian methods. And when you do that, you can kind of completely make the Hamiltonian block diagonal. So you kind of take that 9x9 and you kind of define an effective Hamiltonian, and that effective Hamiltonian has a lot of nice properties. But one of the important ones is that the remaining non-stochasticity is not curable by single qubit rotations restricted to that 2-dimensional effective subspace. So that was a long answer, Daniel. Did that clarify or not?
Yeah. So just to summarize, you are starting from 2 3-level systems. You construct the corresponding 9x9 Hamiltonian. You block diagonalize it using this Ravi method, and into a 4x4 and a 5x5 block. And then the claim is that if you were to try to cure the upper 4x4 block using just qubit operations, single qubit rotations, that would not be possible.
That's right. Okay.
Thanks.
Yeah. But it is kind of curable by using single qubit transformations that are 3x3. So that's the interesting part of it. Alrighty. So since I don't have a mathematical framework that kind of says which kind of Hamiltonians are multi-level curable, right? I don't quite know how to look at a given Hamiltonian, just a 2-level approximation, and effective Hamiltonian, a 2-level approximation, and then decide, is this multi-level curable? And so I think that here is a list of indicators that an effective qubit Hamiltonian is not multi-level curable. So one of the key things is the ability to implement interactions between qubits that are larger in magnitude than single qubit fields. And this is one of the important technological goals for superconducting qubit technologies in general, is to be able to generate interactions between qubits that are larger in magnitude than any single qubit field. So typically, qubits are at like 5 gigahertz, 6 gigahertz, 8 gigahertz, whatever. They are at some finite frequency. And so in some sense, they have large single qubit Z fields on. And then the interactions between them, whatever, they're 5 megahertz, 10 megahertz, in the context of annealing qubits, sometimes it gets all the way up to 1 gigahertz interactions. But nevertheless, the interactions are smaller than that kind of single qubit Z fields. So one thing that we wanted to target with this technology is the ability to implement interactions between qubits that are larger in magnitude than the single qubit fields. And one of the other things that we wanted was that the defining theory, this kind of multi-level theory from which you are deriving the effective Hamiltonian, is, instead of being stochastic, that it is intrinsically non-stochastic. So that's probably a good clue. Then you want the ability to have independent control of all interactions that are needed. So in this paper of Biamonte and Love, they basically say, here are the interactions that you need, the interaction types that you need in order to implement, that are universal. If you can implement them, they are universal for adiabatic quantum computing. And of course, they need to be independently controllable in order to implement the transformations that Biamonte and Love are talking about. So we want to have that capability to kind of be able to, turn on single qubit fields, turn on two qubit interactions, but we want to have independent control of those two at the same time. And so all of those indicators, those above indicators, are all satisfied for the hardware that we developed here for the QEO program. And I'll explain what that is next. All right. So here is a kind of a more general description, just to kind of give you a little bit more of a flavor of what the Hamiltonians look like that we were engineering as part of the QEO program. I think this is familiar to people that do circuit quantization, but basically you have, you can basically go node by node, and you can kind of assign node charge operators, and you can you also have some Josephson terms, and you'll kind of have some magnetic interactions between currents that are flowing next to each other. You'll have some capacitive interactions as well, potentially. Basically, these Hamiltonians are the kind of the bread and butter of designing superconducting or superconducting hardware. And then basically you can kind of look at the construction of path in Monte Carlo, and I think I didn't get into the chat some of the more recent papers that kind of looked at this in more detail, but there are some complexities with implementing this path integral Monte Carlo. But by and large, it was it was kind of seen that these Hamiltonians should be susceptible to path integral Monte Carlo pretty efficiently. So how do we get around this kind of this kind of efficient simulatability aspect, where we want to build in non-stochasticity at a fundamental level into these Hamiltonians? And we make this following change here, where the offset, where instead of just having a charge-charge interaction through the inverse capacitance matrix, but individual nodes, particularly the nodes that have periodic charge variables, you want to implement offset charges. And then it begins to be in this familiar form where you have your gradient minus a vector potential. And then for the form that we kind of know from our schooling, that is, you can put in magnetic field, and you can start introducing complex phases into your ground state wave function. But again, as I explained earlier, in this case, because your basis itself, your position basis is itself flux, which is already odd under time reversal. And so you end up wanting your vector potential to be implemented with these offset charges. And this is something that this is a kind of is known from the general theory of quantum mechanics, that when you have vortices, kind of flux that can kind of go from inside of a loop to out of a loop, and you have two tunneling paths, you can get Aharonov-Casher interference between those tunneling paths. Right. And so I'll just kind of describe a little bit. We developed, again, in the QEO program, a lot of tools to kind of look at the effective theory. And you ended up seeing that you could kind of build wave functions that were kind of localized in one of these minimums and then one of these other minimums. And the tunneling of vortices across junctions basically corresponded to tunneling of tunneling of wave functions between one local minimum and the other local minimum. And I guess maybe are you not seeing my, I don't think you are showing my here we go. That's better.
We can see your pointer. Yeah.
Oh, you couldn't see my pointer. Oh, okay.
Yeah, but this is better. Thanks.
Yeah. Okay. Yes. Okay. And so what you fundamentally need in this kind of flux space is you fundamentally need the two separate directions along which the wave function needs to tunnel between one minimum to the next. And then what you can find is that in an effective Hamiltonian description, you end up getting a Hamiltonian where you can basically say, all right, one of these tunneling paths is going to lead some sort of define some sort of coupling between a state that's here in this minimum and a state that's in this minimum, and whatever phase it is, I'm going to assign that to be an X-type operator. I'm going to kind of reorient my basis so that that becomes a stochastic, a minus X type operator. But then you find relative to that tunneling path, this other tunneling path has exactly these kind of phase factor, these Aharonov-Casher phase factor. And so it works exactly how you kind of expect. Normally we think about Cooper pairs hopping across junctions, and then having, if you have two paths where Cooper pairs hop across junctions, you can put flux in that loop, and you can basically cause, you can just have a Aharonov-Bohm effect, and you can get things like compound junctions. Well, this is exactly the dual type physics, where you have this kind of loop of these tunable phase-slip qubits, and you have two separate tunneling paths for the flux in and out of this loop. And then you basically bias this offset charge here in the middle, and that introduces this non-trivial phase factors. And so one of the things that you can do now is you can tune this this offset charge to exactly half an offset charge, and then the Hamiltonian of your single qubit basically becomes zero. And those two states in each of the wells, you've kind of balanced this at exactly half a phi naught, and you've balanced this as exactly half an offset charge, and those two states become exactly degenerate. And however, you can still have some residual current that's flowing in these compound junctions. And so if you kind of couple these residual currents through this design here that was demonstrated by Lincoln Lab, then you can actually implement strong non-stochastic XX coupling at the same time that the Hamiltonian is zero, kind of satisfying this condition that I was talking about earlier, where you need your interactions to be strong relative to your single qubit fields. Okay, so there are a lot of challenges with engineering into this regime, and there's a lot of reasons why most research groups don't do things this way. And that's what the story that I'm going to talk about next. And it's basically has to do to a fundamental asymmetry between flux noise power and charge noise power in superconducting qubit systems. So typically, if you measure these noise powers in their characteristic quantum scales, which for charge, it's in the context of superconducting circuits, is the Cooper pair charge. And for a flux, it's in the scale of the flux quantum. And what you typically find is that the charge in these intrinsic scales is much louder after much louder than the flux noise. And then here I've already taken a square root. So if you wanted the actual noise power spectral densities, that's a factor of 2,500 difference between charge noise and flux noise. And it is kind of an interesting fundamental question as to why that is the case. And fundamentally, when you end up looking at the ratio of these noise powers, you end up showing that a lot of times that these differences are due in part to the fact that there are two fundamental impedance scales. Namely, there's a vacuum impedance as well as a superconducting impedance quantum, and that the ratio of those two end up being related to the fine structure constant. So this kind of then sets the kind of the as your kind of noisy environment is kind of sloshing back and forth and generating noise for your qubit system, you actually just it just kind of naturally sloshes more into the charge sector than it does into the flux sector, which is a nice intuitive understanding of what is causing this. Although I don't think that there's been a ton of theoretical proof that necessarily the noise asymmetry always has to be there. It's just kind of has this kind of heuristic level, as well as a fundamental difference between the permeability and permeativity, i.e., when you have a magnetic field going through a dielectric, it doesn't change very much. But of course, if you have an electric field going through, you kind of have these bound charges that end up screening, and which dramatically change the kind of the effective epsilon of a medium. And that's another reason why the characteristic impedance scales is that you end up working with in circuits is typically even much lower than the vacuum impedance ends up being like 50 ohms and maybe even smaller. So that only makes the problem even worse. So
David,
yeah, go ahead.
Question.
Yeah.
If I were to translate this observation to standard, poly sigma x sigma z type language, are we saying that the sigma z noise is weaker than the sigma x noise?
That's right, exactly. And so if you kind of go and you try to make this type of Hamiltonian where you kind of revealing all of these X-type operators, there's just going to you're just going to be making yourself sensitive to this, this tidal wave of noise, and that's why people don't engineer into this regime very often. Yeah. So I'm taking to heart, Daniel, that I could go slower than the 30 minutes. So one thing that I really want to emphasize is that here's an example of a, of course, it's kind of harder to look at these diagrams and kind of fully reveal where are the kind of the shunt capacitors and where are the junctions and stuff. I'll have you trust that over here is one facelift qubit over on this left-hand side, and on the right-hand side is another one of these facelift qubits, and we have a tunable coupler here that basically is coupling the current that's flowing in these kind of compound junction loops. These type of compound junction loops in this qubit and this qubit, and we have this way to kind of tunably change the strength of the coupling between them. So not only can we, by adjusting this offset charge, or indeed by the static fluxes that are through these loops, do we have a method of independently adjusting the single qubit fields of this qubit, but these circuits have the ability to tune the XX interaction between these two qubits. So one of the fascinating parts of the QEO program is, of course, the priorities changed over time. And early in the program, Daniel will remember that we spent a lot of time kind of deciding how to generate these XX couplings and hardware that did it, but like the priorities kind of shifted, and these circuits were actually never tested. So there's actually a great shelf of old chips, some that have been fabricated and never tested. So I hope if some experimental lab gets up the courage to try and begin exploring again this kind of non-stochastic regime, and I hear rumblings that a couple of research groups are kind of interested in this regime because there's only so many experiments you can do with a transmon. That I certainly welcome people kind of reaching out to us, or maybe reaching out to Lincoln Lab and figuring out whether we can set up a collaboration where some of these old parts that were very carefully engineered but never tested. So if people are interested in potentially testing these, I hope maybe this is an audience where I can perhaps find somebody that's interested in doing that. So we did demonstrate a single qubit. We did a number of single qubit demonstrations with these facelift qubits. We did show that it was possible to anneal them, so that just like a regular conventional facelift qubits, you could kind of do this kind of fundamental annealing transformation that D-Wave does all the time. And we were able to reveal, some aspects of the offset charge tuning. This isn't obviously great data, but it does kind of reveal that, hey, we were on the right track there. And I think that if you kind of combine this approach with some of the kind of the modern ideas that are kind of coming out of the Matt Bell group at UMass Boston, these bifluxon qubit type of experiments, where they kind of really showed how to create designs with dramatically lower at least quasi-particle noise, that I think that that it can be that these experiments can be taken much further, and it would be great to get something with much lower quasi-particle noise, but it still remains annealing compatible. I think that that's a very fascinating regime in which to push this technology forward. Okay, so I'll just say that, of course, Daniel's big QEO team, we did a huge amount of work where we kind of had tools that extracted effective Hamiltonians, and so we were able to kind of show that, really you could have two independent lattice of interaction channels, and kind of engineering these type of systems where you would have not just a JIJ, a ZIZJ type of interactions, but KIJ, XIXJ type of interactions were indeed possible. Of course, there's going to be some constraints as you kind of define your annealing schedule as to what these amplitudes could be. But we did a lot of simulations to kind of project where you might get to various interesting points of how you might do annealing, how you might keep the interaction strong, et cetera, et cetera. So I think this is a really exciting area for potential development. And just to kind of wrap up here, one of the things that I think is quite interesting, number one, we kind of talked during this talk about like, well, on some level, if you want to do true adiabatic ground state quantum computing, at some level you are going to have to fight this battle of non-stochasticity. You're going to have to develop some hardware that has non-stochasticity. That's a good reason to do it. I think that there are some interesting ideas. I think I posted in the chat there a talk by the Warburton, or an accessible talk by the Warburton group, and probably has some of the citations in there to some of Vicky Choi's work that actually show that in an annealing context, although it's not generic, non-stochasticity doesn't generically help you. There are situations, particularly with avoided level crossings, where you can kind of see some enhancements due to non-stochasticity, and I think that there's some interesting use cases where you could use non-stochastic effects in conventional annealing. But here's an example where I think that non-stochastic effects can really shine, is kind of when you take these type of phase qubits, and again you kind of turn off their single qubit fields, and you kind of create interactions between them, and you kind of can dramatically suppress the sensitivity to noise. So you kind of, it's like one of these one step backwards. You kind of make a phase qubit that at a fundamental level becomes sensitive to charge again, but then by kind of engineering them into this regime where they kind of have these strong interactions, the effective qubit that you kind of are generating in the system then itself becomes immune to noise. And I think, I have a citation here from Daniel's group where they kind of looked at, okay, well, if you have these kind of encoded qubits, you still need to have interactions between them in order to implement quantum annealing, and they kind of discuss how to do that in that paper. And perhaps some I think there was a series of papers there. So I'll just kind of give my conclusion here to say, I think that, as we're, and I'm really, I'm sorry that the time doesn't work out for Paul Warburton to be participating live. Perhaps he'll watch the video later, or somebody from his group will, and kind of challenge me on this. I think that he has a bit of an alternative perspective on this table, so don't take it, certainly take it as my strongly held opinion. But there are others that kind of would have an alternative viewpoint. But if you want to really engineer non-stochastic effects into your hardware, I do think that you need to go to this kind of inductive and capacitive coupling of fundamentally non-stochastic qubits themselves, and they kind of satisfy all of the kind of the requirements that we kind of discussed up at the beginning of things that you would want to have in fundamentally strong non-stochastic system. Whereas if you just try to take existing flux qubit context, existing flux qubit concepts, and just kind of add in standard inductive and capacitive coupling, you can get small residual non-curable non-stochastic effects within within the effective qubit Hamiltonian. But is this a promising route to independently controllable, strong non-stochastic interactions that are sufficient to do universal adiabatic ground state quantum computing? I would say that that's not a direction to go for that. Whereas I do think that down here, these kind of reintroducing charge noise sensitivity and Aharonov-Casher effects, I think, are a quite promising direction to go in the future. And let me just take this moment. Sorry, Daniel, but I'm a little bit over. But this QEO program was a fantastic program, and its follow-on programs as well. I just want to take this chance to thank USC and IARPA and DARPA, as well as all of my Northrop Grumman colleagues and the QEO team and the whole annealing community. You know, D-Wave is always keeping you on your toes. It was just a fantastic project to be part of over these years. And hopefully we'll have a new generation of researchers that get inspired and try to push this technology forward into the future.
Great. Thank you very much, David. And we have some time for questions if the audience would like to pose any. So, David, you brought up this really interesting point about the asymmetric noise.
Yeah.
In terms of Z and X, and as I'm sure you know, there's a lot of work on how to take advantage of this kind of a bias in the noise in terms of improving fault-tolerant quantum computing. So I was wondering if you have any thoughts on whether we can take advantage in terms of error suppression, since you talked about it, in the same sense. Trying to suppress, emphasizing suppression of the X, the charge noise, I guess, over the Z flux noise.
Yeah. So in some sense, I think that, let's see here. There we go. Well, yeah, I guess there's nothing really on this slide. But in some sense, I would say that the transmon qubit is basically is what allowed superconducting technology to actually progress, because it has a fundamental noise asymmetry in the sense that, relative to, say, the charged qubit, well, I wouldn't say it has maybe not a fundamental noise asymmetry, but it certainly has a fundamental noise suppression relative to the charged qubit. So, the charged qubit is basically DC sensitive to charge noise, and of course, I'm just kind of giving characteristic flux noise power amplitudes at an equivalent frequency. But basically, of course, at the very lowest frequency, these noise powers keep going higher and higher, like kind of 1 over f or by 1 over some characteristic exponent power. And so in some ways, engineering transmons into that regime where they become insensitive to the loudest, at least the DC part of the loudest part of the noise, was the thing that made this technology completely take off, whatever it was, 8 years ago, 10 years ago. And so in some ways, you kind of have to undo that all and kind of go back to square one and start engineering qubits themselves that have this sensitivity again, and everybody immediately yells no. But I think that in some ways you kind of have to undo this and become sensitive again. But I do think, by and large, Daniel, though, I think that that is kind of like the story looking backwards. The story looking forwards, I do think there are some really good reasons to think that this kind of observation of becoming, taking the loudest parts of the noise and becoming insensitive to it, is a promising direction to go in to engineer systems, I think is indeed the case. And in fact, it is kind of an area that Yale is showing is quite promising, and a number of groups are showing it quite promising. So yeah.
Okay. Any other questions from our current participants? All right, if not, well, thank you for that great overview, and it was very nice to be reminded of all the work
All the work we did.
all the work we did under QEO and QAFs, and I hope that that will continue.
Yes.
So thanks again, David.
Yep. All right. I'll talk to you later,
All right.
Daniel.
Bye-bye.
Bye-bye.